Hey there everyone, this is the final video in our Stats 1020 overview in preparation for the final exam. In the last video we reviewed all the hypothesis test sections, and prior to that we reviewed chapters 6 through 9, which dealt with a little bit of inferential statistics, normal distribution, sampling distribution, and confidence intervals. And prior to that we reviewed chapters 1 through 5, which dealt with a lot of the preliminaries to statistics. Descriptive statistics, reading those graphs, and of course the numerical analyses that we can have, looking at means and standard deviations and measures of relative position. We looked at probability and of course probability distribution. So this is a kind of a nice short video here as we finish up with chapter 12, which dealt with correlation and linear regression. So we covered two sections here, and it's kind of a nice way to sort of end our work in the course. And so this particular chapter begins with looking at variables, two quantitative variables, and making some comparison here and asking ourselves, can we really tell whether or not there is a relationship, a possible relationship between these variables? And we do that using a numerical computation known as the correlation coefficient, which we'll get into in just a minute. So there's a way to kind of look for a relationship visually, and we use what's called a scatter plot. So we look at something we think of as the explanatory variable, which we hope explains the response variable, which is the dependent variable. And so that's what we're looking at here. Now to graph on the scatter plot, we do have to use our xy axes, and we do have to use ordered pairs, and the ordered pairs take on an explanatory comma response order. Okay, so that's the x comma y. Okay, and remember, in a scatter plot we do not connect the dots, and we do abide by all those wonderful good rules that we had on what makes a graph good. So making sure there's a title, labels, equal increments, a key if necessary, etc. And what we do, we look at scatter plots and we ask ourselves, do the data themselves lie in a line? This is what we call a linear relationship. Sometimes things don't lie in a line. Maybe they are representative of something else, maybe a parabola, and if so, then that has some implications for us as well. Or maybe they look as exponential. Okay, so it just depends. But what we're looking here in this set of sections is linear patterns, okay, a direct relationship in that way. So we've got ways of calling it a positive association. If things look from left to right, that they're going up. If going left to right, things go down, the points go down or appear to go down, then we have a negative association. And so it's all well and good to describe these things in words. What we need to do, though, is put a numerical descriptor to it, and that's what gets us into this correlation coefficient, Pearson's correlation coefficient, which we denote by the letter R. And so that deals with the sample, and if we were talking about the parameter, we would use the Greek letter rho. So that's how that works here. So R is a value that ranges from -1 to 1 inclusive, which means we can have a correlation that is exactly equal to 1 or -1. So the stronger, we say the stronger the association means that we are closer to 1 or -1. So if we're closer to 1, we've got a strong positive association. If we're closer to -1, then we've got a stronger negative association. And if we get closer to 0, then we say there is no linear relationship. So we can't use correlation coefficient if the data itself does not resemble a straight line relationship. Okay, it's useless. We have to try something else then that's maybe covered in other courses. We have to be careful of outliers that can influence the calculation of R, and the reason for that is the correlation coefficient relies on the mean in its calculation, and so if there's an outlier, we know that outliers do impact the mean, and so as a result, correlation as well. Now, just because we have two variables that are correlated does not mean that they are actually in a relationship where one causes the other. Okay, so you kind of have to take it, as a leap of faith, that just because you're seeing that there is a correlation here, you kind of have to perform this experiment to really study a cause and effect relationship. So the correlation kind of suggests to us that there is a relationship, and then we can make our decision based on that in looking at possibility of doing some additional study. Make sure you understand how confounding works with lurking variables. Okay, it might be something else that's causing the reaction in the variable. We talked about that in chapter 1. And of course, just to remind everybody, you do need the comparative experiments to help reduce the influence of those lurking variables. And that's all stuff we talked about before. We've got something called the the coefficient of determination, which is based on R, the correlation coefficient. And this very simply is R squared. And this is a measure of the proportion of the variation in the response variable, y, that can be associated with the variation in the explanatory variable, x. And we did talk about this in the slide, so make sure you go back and take a look at the notes. And if we're talking about how I word this in an exam or the final exam, of course, it can say what percent of the variation, blah, 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 or how much of the variation in blah can be explained by blah. And so that's how you know you got to find R squared. Sometimes the question might just say, what is the coefficient of determination? Okay, if so, you have to remember that that means R squared, so don't forget. In section 12.2, what we did is we said, okay, well, if we've got a scatter plot and the data resembles a line, we're all about making predictions. And so what we can do is create an equation for this line, this modeling line. So the line is a special name. It's called the least squares regression line, or LSR. And again, it helps us to make predictions. It's written in this mx plus b form, which everyone is familiar with, the slope-intercept form. Okay. And once we know what that equation looks like, we can make some predictions. And so there were some formulas that were presented in the slides from this section, so make sure you go back and you take a look. Now there is a caution here for the second to last bullet point, which says we have to be aware of extrapolation. What this means is that sometimes we may try to stretch our model by making a prediction that is outside of our data. Okay, we can't do that, so some limitations to this equation. So it's only good to make predictions of our data within the cluster of where the data is. So we can't try to predict something that's way outside of it. It's going to cause some issues. Okay, so some people test the limits of that by doing predictions on the peripheral, if you will, of where that data lies, and even that can have some risks to it. So just to be careful, okay, in how you use that line. And we did talk about how to interpret the slope of the least squares regression line, so make sure you take a look at that. There were some examples that were worked in class. And so that really completes the review as Master Yoda is revealed to you. So the question is, was that everything? So don't forget, there are materials posted on Canvas, the old final exams. Okay, make sure you take a look at those. There are some extra worksheets and things with some solutions there as extra practice for you. And don't forget about the cheat sheets. There are 3. One is on graphs, one is on confidence intervals, and the other is on hypothesis tests. And so it does a nice little summary of the formulas and some of the other important concepts, okay, that were important to us in the course. So that's it. That's the comprehensive review. So hopefully you've been jotting some things down that you might have to go back and take a look at as you begin your studying for the final exam. So that is it. All the best to you on the final.